Hi, welcome to Unacademy. Unacademy is the India's largest online learning platform. Now we are happy to announce that we are going to training the students for GATE and their engineering service examinations. About myself, I G Venkata. I have 16 plus years of teaching experience. So far I mentored more than 60,000 students for their GATE examination. At present I am pursuing PhD from JNTU Kakinada and my specialization is VLSI. First, we check how to get the Unacademy Learning app into your device. See, if this app is in your device, it's fine. Otherwise, by following this procedure, just install this app in your device. Just type Unacademy in your Play Store. Just open your Play Store and type Unacademy in that. Then you get the Unacademy Learning app like this. Okay. Just click on this install button. Once you click on this install button, it will install the Unacademy Learning app into your device. Okay, and after that, once you open this app, you will get what are the different courses available in that and who are the top educators handling the courses in that each subject. And if you want, you can get the brief introduction about faculty also. Okay, so my dear students, please don't miss this opportunity. India's top educators are available here. Okay, please take the services of them, utilize their services and get success in your career. Now if you check few of the top educators, Tiwari sir, he is a topper IIT. Ankit Goyal sir, he is a 2 times GATE electrical department all India topper. And Jain sir, he is the having more than 8 years of experience in computer science. And Jaspal Singh sir, he is the ex-IAS officer. Okay, and a few more top educators here I am introducing. See, for civil engineering, general studies and aptitude, instrumentation engineering, civil engineering, mathematics, mechanical engineering. Here are the few of the top educators. Now, I am happy to announce that there is a new batch we are going to start for GATE 2022 and 2023 students. That is a Ascend batch. This batch is started from 8th February 2021. This is for mechanical department. Next, there is a Evolve batch for GATE 2022. This batch is for mechanical department itself. It is going to start from 8th February 2021. Here you are getting from top faculty who are going to handling the subjects in that department. Next, for civil engineering, there is a GATE Ascend batch. This is for GATE 2023. This is also going to start from 8th February. Next, there is Evolve batch for GATE 2022 civil engineering. New batch it is. It is started from 8th February. And there is again Evolve batch for GATE 2022 computer science and information technology. This is we started this batch from the request by receiving more number of requests from computer science students. This batch started because even though that much demand in outside for software engineers, software field, okay, but most of the students are turning towards to write the GATE examination. Okay, that is the importance of the GATE. Once they crack the GATE, they move into toward the IITs, and in IITs life is different. Okay, now this batch also started from 8th February. Now there is a Ascend batch for GATE 2023. This is for electrical engineering. Here are the top educators who are handling the subjects in this electrical department. This batch started from 1st February 2021. And there is again Ascend batch for GATE 2023. This batch is for electronics and communication engineering. This batch is started from 1st February 2021. And there is again eval batch for GATE 2022. This is for electrical engineering. Here are the top faculty who are handling the subjects in that, and this batch started from 1st February 2021. And there is a eval batch for GATE 2022. This time this is for electronics and communication engineering department. This batch started from 1st February 2021. Next, there is a batch for eval batch for GATE 2022. This is for chemical engineering. Okay, now this batch started from 25th of January. So my dear students, please inform this one to your friends if anyone is doing the chemical engineering, because at outside it is very difficult to get the chemical engineering training for GATE. So you must thank to Unacademy to provide such a beautiful faculty for providing the GATE training to you. Okay, and don't forget to use my code VRAU10 during subscription. VRAU10 during subscription. By using this code during subscription, you get 10% discount. Next, see, these are the overall different courses available from Unacademy for GATE and service examinations: mechanical engineering, electrical engineering, civil engineering, production and industrial, instrumentation engineering, chemical engineering, computer science and IT department, last but not least, electronics and communication engineering. Okay. Now, here there are two types of subscriptions available for engineering and GATE and engineering services. The first one is plus subscription. Second one is iconic subscription. Analyze the test what you've written, and after that they will prepare a note where you are strong, where you need more preparation, okay, where you are doing mistakes. Even though you prepare the topic, where you are committing mistakes, they will prepare the data. Okay, based on the data, they will prepare a proper study planner to you. Okay, and proper study material to you. By using these two effectively, by following these two effectively, a student definitely can crack the GATE examination or service examination. Okay, don't forget, compared to plus, iconic is more useful in the point of view personal coach. Okay, for the students who are studying third year and final year, okay, for them this is suggestible. Who are completed BTech, okay, they can manage this one also, it's not an issue. Okay, because the students who are studying third and final year, they are busy with their regular college work. Okay, they are unable to analyze their test what they've written. Okay, that's why this is the best course for them. Now if you check the cost for each and every subscription, that is a nominal cost. So for plus subscription, the cost of plus subscription is for 1 month it is 5,500, for 3 months 13,750, like that. For 1 year it is 30,000. 1 year it is 30,250. Okay, for 12 months it is 27,225. 27,225. Okay, so by paying this much amount, you can get the complete full year access. Okay, 1 year access. So just 2 days before GATE exam was completed, I think so, by seeing the paper and after completion of your examination, I think so you got some idea where you are. Okay, please don't disappoint. Okay, and probably next July you have a service examinations, try for that one also. And meanwhile, don't waste your time, continue your preparation. Okay, please don't give rest for learning process. whatever thing is happened, your learning process should continue. Okay, so my dear students, by joining these plans, continue your learning process here. So you have different subscriptions, 1 month, 3 months, 6 months subscriptions. Choose whatever the subscription suitable for you, join in that and continue your learning process. Okay, and get success in your career. The cost, if you observe the cost of this one year, 27,225 rupees. It is just 2 or 3,000 more than the amount what you need to spend for traveling from your home to the location where you need to take a coaching. Okay, so if you join somewhere at outside for taking the coaching, now to travel from your home to that location, you need to take some travel assistance throughout the year during public holidays, weekends. So for that, throughout your year, you need to spend more or less that much amount. Okay, just only this is close to the transport charge. And the next case, there is a iconic plan. There is a iconic plan. Okay, so this iconic plan is for 12 months they are charging 50,000. Okay, now after using my code, they will charge only 45,225 rupees. 45,225 they will charge only. Okay, don't forget to use my code VRAU10. And once again, I am remembering you, I am telling you, in Iconic, we provide a personal coach to you. That personal coach behaves like a guide to you. Okay, he will analyze the things what you done in previous examinations. Okay, he will suggest the proper way, best way to you to success in your life. Okay, so my dear students, don't waste your time. Whatever thing was happened, leave it. Now concentrate on future. Okay, don't be disappointed even if you not attempted GATE properly. Okay, without wasting time, join here and prepare for next year. Okay, definitely you will crack the GATE, no doubt at all. Okay, so just we will provide the support for that support to you. Just follow the instructions which were provided by our team. Okay, thank you very much for this, for your support. Now we are going to moving to today's topic. Now our today's topic is biasing of PN junction diode. Already reverse bias of PN junction diode is completed. Now I am going to forward biasing of PN junction diode. Okay, so now we are going to forward bias. Forward bias. Forward bias I am going to. Okay, now we know what is forward bias. Simple. This is the circuit diagram for that. So PN junction we have, and there is a resistor in series with the diode to provide a security to the diode from sudden variations from power supply. Now this is positive and this is negative. P side connected to positive, N side connected to negative. Okay, P side positive and N side negative. So this is forward biased diode. Now you can take it as a forward voltage or diode voltage, VD. Okay, now so once P connected to positive, N connected to negative, an electric field is directed from P region to N region. Okay, so once you use the term electric field, now I am going to writing the PN junction in a regular one. That means in terms of P region and N region. Okay, so now This is P region and this is N region. At the time of open circuit condition, we have a depletion region at P side and a depletion region at N side. So let us, I am taking P plus N junction. Default it is P plus N junction. Now here a negative immobile ions are there, and here we have positive immobile ions. So an electric field is directed due to this from N region to P region. Now here you are biasing this, just connecting P side to a positive terminal of the battery and N terminal connecting to negative terminal of the battery. Okay, now the applied voltage I am taking it as VF, forward voltage, let us. Okay, so due to this side became positive, it became negative. Now an external electric field is applied in a direction P to N. Okay, now the net electric field is opposite sum of these two, but here see, this is the junction electric field, what is existing at the junction at the time of open circuit. Now I am representing that one by E naught. This is the electric field due to forward bias. Let us take it as EF, electric field strength by applying externally, EF. Now the net electric field is written as net electric field. Both are opposite in direction. Therefore EF minus E naught. EF minus E naught. Here E naught is constant. Okay, but EF can vary by varying the applied forward voltage, VF. By increasing applied forward voltage, the strength of the electric field is going to be increasing. The strength of the electric field is going to be increasing. Okay, now here what happens, just check it. For low values of forward voltage, EF, external electric field strength, is low. For that low electric field strength, okay, this is positive. With respect to this, holes has to try to move from P region to N region, and electrons are try to move from N region to P region. But this movement is opposed by this electric field E naught. Due to this opposing force, even though more number of majority charge carriers available in P region and more number of majority charge carriers available in N region, here we get only very few number of carriers cross the junction. Okay, so that if you want to say strictly, that is negligible value. Okay, negligible value. So by increasing the applied forward voltage, that means here E naught is going to be dominating compared to EF. E naught is more greater value. Now by increasing the applied forward voltage, what happens is, by increasing applied forward voltage, EF is going to be increased. Once EF starts increasing, the net electric field what you written here is going to increase, because initially it is a negative, because it is low value, it is high value, it is negative. Okay, now the net electric field, once EF is increasing, net is going to be increasing. So the net electric field is directed this side. This is the E net electric field. Okay, now once so by increasing EF continuously at one particular value of VF, EF is equals to E naught. EF equals to E naught. At this point, the net electric field is 0. Net electric field is 0. At the same time, there is no depletion region. No depletion region. Because carriers just entered into this depletion region. Holes just entered into this P side depletion region, and electrons just entered into N side depletion region. Once that region covered by, once the charge carriers entered into the depletion region, then you can't say that is a depletion region. Depletion region means it is filled by only immobile ions. There is no charge carrier. But due to increasing in the forward voltage, holes entered into this depletion region on p side. Similarly, electrons entered into the depletion region of n side. Okay, so due to this, you can't say that no depletion region is existing at junction. Now the depletion region is approximately 0. The width of the depletion region is approximately 0. Okay, can't say exactly 0. At a given stipulated time, there is a chance of existing little bit negligible value of depletion region. That is not considerable value. Okay, and after that, if you are going to increasing the applied forward voltage, now EF is now greater than E naught. Okay, therefore E net is going to start increasing. Okay, and more net electric field is there. Net electric field is directed from P to N. Now holes will move from P region to N region. Similarly, electrons starts move from N region to P region. Okay, this movement provides more conduction to you. Okay. Now, by increasing this applied forward voltage, this movement of the carriers is increasing. Now, current is going to be increasing continuously. Okay, now this is the way of writing the its VI plot. This is the VF forward voltage and forward current IF. So, see, up to some voltage, you need to apply a little bit forward voltage to nullify this effect of E naught. So, up to this, let us say take this value. Okay, up to this much I want to apply to nullify the effect of E naught. So, up to this point, there is no current. There is no current. After this, approximately depletion width is 0. Now, once the depletion width is going to decrease, few number of charge carriers try to cross the junction. Once a few number of charge carriers crossing the junction, now the current is going to increasing slowly, and after that increasing high. Okay, now this is the maximum current. Now 10% of maximum current, let us take somewhere here 10% of maximum current, maximum rated current. Now this is called as V gamma, cut-in voltage. That means the minimum forward voltage required to make the PN junction diode into on state or conduction. Even though forward voltage less than EF, your diode is forward bias, no doubt at all, but there is no current. That current is not considerable value. After V is applied forward voltage greater than V gamma only, the current value is considerable amount, and that value of forward current is of the order of milliamperes and the voltage is of the order of volts. Okay, this is the forward characteristics of voltage and current, VI characteristics of a diode in forward bias. Okay, so is it clear? Now from this forward characteristics, later we have a separate session for complete analysis on VI characteristics. From VI characteristics, what we have to analyze and what we get, what we gain, what knowledge we are going to gain from the VI characteristics of the diode, and how to take the voltage and how to take the current values in lab, and everything we discuss in later sections. So this is the VI plot finally. Okay, now I am going to discussing about first what are the different diode current components. Okay, like in terms of drift and diffusion current components. So diode current components. Current components. Okay, here what I am doing is I am taking the diode. So this is our diode. And this is junction. Now depletion region width, because our diode is in forward bias, that's why I'm not considering the depletion region width. So this is P region and this is N region. So this is connected to positive terminal of the battery, positive terminal of the battery, and it is connected to the negative terminal of the battery. Now, before going to that, I'm going to just considering the available charge carriers. In P side, let us, these are the number of available charge carriers, available electrons, minority charge carriers in P region, and these are the available minority charge carriers on N side. That means now in general we are writing this one by P N naught, and this is N P naught. N P naught. So the meaning of this one is hole concentration in N region under steady state. This is electron concentration in P region under steady state. Just before we mentioned the minority charge carriers. You may ask one thing, sir, why don't you take in both are equal? See, both are not equally doped. If both are not equally doped, then I have to take both are equal. Both are uniformly doped, that's it. Not equally doped, just both are uniformly doped. Okay, just a minute. Now, see this here. So once it is okay, now P side we are connecting a positive and N side there is a negative. For better understanding purpose, now first I am going to completely discussing on one side what happens. Later I will apply that one to other side also. Now once it is positive, whatever the holes, majority charge carriers available in P region, they are very high in number because they are majority charge carriers. Okay, these holes are going to be move from P region to N region. Why they are moving? Because there is an external electric field which is directed from P to N. In electric field point of view, an external electric field takes place from P region to N region. That means it is directed. Due to that, whole movement should be in the direction of electric field. Because of that, holes has to move from P region to N region. Okay, they are moving. That means now here whole movement is due to electric field. Okay, so now the whole movement here I consider it as drift movement. Drift movement of holes are moving this side. Fine. By holes moving this side, this much number of holes entered into junction. This much number of holes entered into junction. This much number of holes entered into junction. Now they cross the junction. That means they entered into N region. They entered into the N region with a movement of drift movement. Fine. Now this much number of holes are there here. But in N region, if you observe the N-type semiconductor, this is our N-type semiconductor. In this, at a junction x equal to 0, this much number of holes, and at the far end of the n region only few number of holes, Pn naught. Okay, that means there is a concentration change with respect to distance in n region of holes. So that means at a junction more number of holes, and at extreme end of the n region less number of holes. Due to this concentration gradient, holes are moving from high concentration region to low concentration region. We called it as drift moment, the diffusion moment, because here movement of the carriers is due to concentration gradient. Now we called it as diffusion moment. Diffusion moment. Okay, now holes try to move this side, but the way how electrons are available, holes are available in p region as a majority charge carriers, similarly electrons are available plenty in n region because they are majority charge carriers. Okay, now don't forget I will take a p plus n junction. Now once more number of electrons are available freely, free charge carriers, during this movement your holes are going to recombine with the electrons which are available in n region. So due to that recombination, that pair is going to be disappear. That means it is forming a covalent bond, and it's by moving towards this, recombination is taking place. After diffusion, recombination taken place, now whole concentration is going to decrease like this. Finally it reaches the steady state value. We don't know it takes how much time, how much distance they are traveling, so they are going to be moving like this. Okay, now this is the distribution of hole in n region. Okay, now first we go and check what are the sequence of events taken place in a forward biased PN junction diode. The first event taken place is holes are drift in the P region. Okay, with the drift movement they enter into the N region. Once they enter into the N region, there is a concentration gradient in N region due to holes. Now due to that concentration gradient, holes are moving, that means a diffuse towards the extreme end of the N region. Sorry sir. So here they are diffusing from high concentration region to low concentration region. During the diffusion movement, due to availability of large number of free electrons in N region, those holes are going to recombine with the electrons. Okay, once recombination taken place, that concentration of holes is going to be decreased with respect to distance. Now decrease, see this, it is exponential way. Okay, now the sequence of events taken place is, sir, this is the previous GATE question, sir. What are the sequence of events taken place in a forward biased PN junction diode? That is the previous GATE question. The first event taken place is a drift. First event taken place is a drift. Second event is diffusion. Third event is recombination. And you observed or not, whenever you have a diffusion, immediately there is a recombination. These are the sequence of events takes place in a forward biased PN junction diode. Drift also called as injection. Drift also called as injection. Okay, so these are the sequence of events takes place in a forward biased PN junction diode. Okay, so far what we completed, just what are the charge carriers and how this charge carrier movement is there. Okay, that one we completed. Now I'm going to applying this one this side also, and at the same time, once electrons is very large in number, now this is the electron concentration. Once electrons are moving this side, this side due to this negative. That means electric field is from P to N. Now electron movement should be N to P. The way how your holes are drifting in P region, the same way electrons are drifting in this side. But in this drift movement, electrons are recombined with the holes which are coming opposite side. Now this is going to be, that's why its concentration is going to decrease. Okay, and finally this much number of electrons entered into the P region. Now again they are due to high concentration of electrons at this junction and low concentration of electrons at the extreme end of the P region. Electrons try to diffuse in the P region like this. Okay, once they diffuse in this direction, now they recombine with the holes which are available. Now its concentration is going to decrease like this. Okay, now this is the drift movement, this is the diffusion movement of electrons. Similarly here there is a drift movement of holes, okay, drift movement of holes and diffusion movement of holes. So this is the movement of electrons. Okay, so hole drift current in P region, electron diffusion current in a P region, electron drift current in N region, hole diffusion current in N region. These are the different current components. Now I am going to next. Now I will define these current components in detail, because we know why this mechanism is taking place, how it is taken place. Now see, for a differentiation purpose I am taking a very small amount of depletion region, very small amount. Okay, for a differentiation purpose, clarity, for better understanding purpose. Okay, so now this is a P region and this is N region. Okay, so P region and N region, P connected to positive and N connected to negative. Under steady state condition, these are the number of holes, number of in P region minority charge carriers are electrons. These are the number of electrons in this region. Similarly in N region, these are the number of holes, minority charge carriers. Now this concentration value is, we are representing this one by NP0 and PN0. NP0 and PN0. This is NP0 and this is PN0. Okay, now let us, this much number of holes are entered into the N region from P side. This much number of holes are entered by diffusion, sorry, by drift. Now these holes, this is the hole concentration at junction, now very high in number. Now at this end hole concentration is very less. Now these holes are try to diffuse this side. During this diffusion process, what happens is, whatever the electrons available there, electrons available in N region, see, electrons available plenty. Now by recombine with that, hole concentration is going to be decreasing like this. After some time, by traveling some distance, they reach the steady state value. That's it. Okay, and electrons are moving this side. So electrons are moving this side, don't forget. Electrons are initially this much. Up to this point there is no recombination, because At this point, this is end. Now no recombination up to this point. From this point onwards, there is a recombination. So by recombination, due to that recombination, its concentration is going to be decreasing like this. Okay, do one thing. So they are very small in number because it is a P plus N junction. So they are very small in number. So okay, now very small number I am taking. So its concentration is going to be decreasing. Concentration is going to be decreasing. Now this much number of electrons entered into the P region. Okay, once this much number of electrons entered into the P region, here high in number electron concentration, now here low concentration, due to that electrons are diffuse like this. Like this. Now with respect to hole, in hole point of view, see holes are moving like this, they are drift. Once they reach this point, from this point onward there is a recombination with electrons. Now due to that recombination, hole concentration is going to decreasing and reach this value. Okay, this is the carrier moment. Now here, once holes are moving this side, this is the hole movement. Okay, this is the electron movement. Electrons are moving this side. Okay, so I'm writing that this is the hole movement, holes movement, and this is the electrons movement. So here also electrons, here holes. Okay, so once holes are moving this side, there is a current due to this hole movement. That current I am taking as IPP of X. So there is a current in this side, okay. Now hole current, this one, and there is a this side also there is a hole current. There is a hole current. Similarly, electrons are moving this side. Due to the movement of electrons in this side, there is a opposite direction, there is a current. Okay, now that current is opposite direction, this side. Similarly, this side. Okay, now I am giving names to this. This is the current IPP of X, and this is the current IPN of X, and this is the current INN of X, and this is the current INP of X. This is the junction, sir. You consider it is x-axis, this is 0, x equals to 0. Okay, and it is the carrier concentration. Now IPP of X is this is the whole movement in P region, that is the drift movement already we mentioned. Now IPP of X is the whole drift current in P region. So first current component is IPP of X, which is whole drift current in P region. Whole drift current in P region. Okay, similarly second component is I n n of x. I n n of x. This is electron drift current in n region. And third component is I np of x. That is electron. See, electron movement here is a diffusion movement. Electron diffusion current in p region. Electron diffusion current in p region. Okay, next we have IPN of x is left. So next one is fourth one, IPN of x. IPN of x is pole diffusion current, pole diffusion current in n region. Okay, these are the different current components in a forward biased PN junction diode. Default current components means it is in forward bias. In reverse bias we have only one current, that is I naught. So here we are going to deriving the expression for that I naught also. Okay, we are going to deriving the expression for that one also here. Now, so these are the different current components. Drift component is there, diffusion component is there, for electron drift is there, hole drift is there, electron diffusion is there, hole diffusion also is there. Now, my intention here is to calculate the diode current. How can I define a diode current? For example, I want the diode current equation in P region, diode current equation in N region, diode current equation at junction, or diode equation current equation at extreme end of P region or at extreme end of N region. How can we write? Now everything, if you are writing anything, that should be in terms of these currents. Okay. Now I am going to writing diode current equations. Therefore, diode current is ID is at extreme end of P region, extreme end of P region, there is no diffused electrons. So electrons are recombined and there is no excess electrons which are coming from N region to P region, or injected electrons which are injected from N region to P region. There is no excess electrons from this point onwards. So that means from here to here the total diode current is IPP of x. Okay, you want any current, diode current from this region to this region, once you are taking, at this point it is sum of this one plus this one, it is 0, and at this point it is sum of this one and this one, at this point sum of this one plus this one, at this extreme this is only equal to this one. At a junction this is INP of x plus IPN of x, PN of 0, that is at junction. Okay, now first ID is equals to, first we can write it is equals to IPP of x only at extreme end of P region, at extreme end of P region, end of P region. P region. Next, second equation for ID is, now I am entering into P region, not at extreme end, I am entering into P region. In this region, diode current is pole drift current plus electron diffusion current, IPP of x plus INP of x. NP of x. This is in P region. In P region, that is. Okay. Next one is, so once we reach that, okay, finally we write the equation at junction. Now in N region, it is INN of x plus IPN of x. INN of x plus IPN of x. This is in N region. It means electron diffusion current plus electron drift current in N region plus hole diffusion current in N region. Sum of these two is the diode current in N region. Next, equals to INN of x at this region, at extreme end of N region. This is at extreme end of N region. At extreme end of N region. Now, another one. At a junction, now I am going to. At a junction, holes are drift and they entered into N junction. Now from that point onwards, they are going to be diffusing, and similar electrons are drift and they are diffusing in the P region. Now IPN of 0, hole diffusion current at a junction plus electron diffusion current at a junction. This is at a junction. This is the diode current at junction. So you can define your diode current like this in terms of these different current components. Okay, these are the different current components in a PN junction diode. Okay, so hole drift current, hole diffusion current, electron drift current, electron diffusion current, like that. Okay, so is it clear? Now, if someone asked you, what is the diode current equation in terms of drift and diffusion? Now, immediately you have to ask one thing. At which region you want? In N region you want, or in P region you want, or at junction you want, or in at extreme end of N region you want, or at extreme end of P region you want? Okay, if they ask like that, it means default. In these expressions, you have to use a default. There is a one equation for default, that is this one, at a junction. At a junction, because at junction both are diffusion current components. Okay, so these are purely diffusion current components. These are drift components. Some drift component is exist in the remaining case. So to get the drift component to use, you need to go for electric field intensity. So that's why we concentrate only on this equation. We use this equation to derive the equation for a diode current. Okay, now I am going to deriving the diode current equation. Before going to that, deriving the diode current equation, what are the different equations or relations present in this N region? Once holes are try to inject into the N region, and once they injected into this and then they diffuse into this, during that process, what are the different equations related in that? Now I am going to first representing that. Okay, so this is the N region. This is the N region, and it is the steady state hole concentration in N region. Steady state hole concentration. This is X. X. This is hole concentration. Hole concentration. P of X. Hole concentration. With respect to distance, this is in N region. N region. Okay. And the value of this one is PN naught. This is also PN naught. Okay. This is N region. Once holes injected into this, let us assume this much number of holes are injected or drifted from P region to N region. So high amount of charge carriers, that means carrier concentration is high at junction at x equals to 0. Now at this point hole concentration is less, so diffusion is taking place. Now holes are diffusing like this. They are diffusing exponentially like this. Finally they reach the steady state value. Okay, now let us take, this is the injected or excess hole concentration at a junction. Injected or excess. This is excess or injected hole concentration. Let us take P dash of 0. P dash of 0 is the excess or injected hole concentration at a junction. Now this is the PN naught under steady state minority carrier concentration in N region. And I am writing another one. This is total hole concentration at junction, P of 0. Total hole concentration at a junction, P of 0. Okay, now if you want to relate these, see this. This is P of X. Now this region, this is exponential one, exponentially decreasing. It is decreasing with respect to distance x. Now the equation for this one is written as total value is P dash of 0, P dash of 0 into e power minus x by, they are diffusing, during diffusion they are recombined with electrons, and the diffusion length minus x by LP, because they are holes. That is the equation for this exponential variation. It is decreasing, that's why I taken it as a negative. So in mathematical already exponential one you represent it like this. Now so I am going to represent in different forms. That is, the first one is P of X is PN naught under steady state, whatever the charge carrier, minority charge carrier concentration, hole concentration in N region, plus this one, plus P dash of 0 into e power minus x by LP. This one. Okay. And second one is P dash of X, that means injected hole carrier, injected hole carrier. This one, only this plot is P dash of 0 into e power minus x by LP. Okay. And the third one is just in this substituting x equal to 0. That is P of 0. Total hole concentration at junction is, it is constant, Pn naught plus x0 you taken. So e power minus 0 is 1. So it is simply P dash of 0 into 1. So you can write Pn naught plus P dash of 0. Now, what are the things here you've written? I am going to be defining all these things. Your first one is P dash of Pn naught. Pn naught is under steady state, hole concentration in N region. In N region. Next, second one is, this is our next P dash of 0. So P dash of 0 is excess or injected, excess or injected hole concentration at a junction. Next, same way I am taking P dash of X. This is excess or injected hole concentration in N region, because this is P dash, not P dash of 0, P dash of X, somewhere here, somewhere here, somewhere here. That is P dash of X. So it is excess or injected hole concentration in N region. Okay, so we covered this one completed, and this one also completed. Next, the remaining is P of X and P of 0. P of X is total hole concentration in N region. In N region. Next one is P of 0. That is total hole concentration at junction. Hole concentration at a junction. Okay, and another last parameter we have, that is LP minus x by LP, there written. LP is hole diffusion length. Hole diffusion length. That is. So these are the parameters, important parameters and important equations and their respective terminology when your diode is under forward bias condition. Okay, so my dear students, this part is very important to get the diode current equation in forward bias. Okay, now I am going to that current equation. So that is Now I'm going to diode current equation. Just I write the introductory part here, and next slide I go to the complete. See, I want diode current. Diode current ID is, I am taking the junction condition at a junction. At a junction, we know it is IPN of 0 plus INP of 0. So we know that IPN of 0 is whole diffusion current. Whole diffusion current at a junction. At a junction. Okay. So now I am going to writing for my easy understanding purpose. I am representing this one by IP. Whole diffusion current now onwards I am representing by IP. Because there is no drift current. Simply we have diffusion current. Okay, that's why I am writing it as IP 0 at a junction. Now we can write that IP of 0 is, because current density we can write current by area. So now I is equal to J into A. So Jp of 0 into area, where Jp of 0 is whole diffusion current density. Whole diffusion current density. Okay, later I will add a subscript 0. Okay, later I will add subscript 0. Meanwhile I am removing that. First we need JIP. Okay, so that IP is Jp into area, where Jp is whole diffusion current. Okay, just to substitute that one in that equation. Therefore Jp is, just before you mentioned it is a diffusion current, whole diffusion current, it is whole diffusion current. Now its equation is, we know that minus dp into p into q into dp by dx. Okay, dp by dx. Therefore ip is minus dp into q into dp by dx into area, that is the IP. Now I am taking dp by dx, but from plot, this is n region we mentioned already, and this is the whole concentration. This is x. Under steady state it has minority charge carriers. Now it is exponentially decreasing. Already we defined the equation for this. Okay, so we know P of x equals to Pn naught plus, this is P dash of 0, P dash of 0 into e power minus x by Lp. X by Lp. This is the equation. Now here I want to dp of x by dx, because here whole concentration varying with respect to distance. This is a Pn naught. I want a differentiation of this with respect to x. Therefore dp of x by dx is, it is 0, it is constant, that's why it is 0, plus p dash of 0 constant into e power minus x by Lp. So it is e power minus x by Lp as usual, into differentiation of minus 1 by x by Lp is minus 1 by Lp. Now its value is, therefore dp of x by dx is minus p dash of 0 by LP into e power minus x by LP. Okay, this is the current. But we need at x equals to 0. Okay, now I am going to that. We need IP of 0. So IP we defined minus dp into q into dp of x by dx into area. Sorry sir. Now I want at x equals to 0, this one. So similarly this is at x equals to 0. So at x equals to 0 you are representing that one is IP of 0, that is minus a into q into dp into dp of x by dx at x equals to 0. Already we derived dp of x by dx, that is minus p dash of 0 by LP into e power minus x by LP. Just substitute x0 in that. Now I am applying the condition on this, that is dp of x by dx at x equals to 0 is minus p dash of 0 by LP into e power minus 0 by LP. So the value of this one is minus p dash of 0 by LP. That's it, because it is into 1. Now take this one, substitute here. Therefore IP of 0 value is, therefore IP of 0 is whole diffusion current is at junction is minus a into q into dp into dp of x by dx. This is our equation, sir. dp of x by dx at x equals to 0. Already we calculated that value. Now substitute that a into q into dp into the value of this one just before we calculated minus p dash of 0 by LP. Now this minus into minus became plus, that is a into q into dp by LP into p dash of 0. That is the next level of equation for diode diffusion current. Okay, now we need to get the value of p dash of 0, the amount of injected or excess hole carrier concentration at junction in n region. So already we derived just before different equations. Now just a minute, I am going back to that. See this here, p of 0 is pn naught plus p dash of 0. Now I am going to using this expression. Here we know p of 0 total hole carrier concentration at junction is under steady state minority carrier concentration plus injected hole carrier concentration. From this, just to take the value of p dash of 0, p dash of 0 is p of 0 minus pn naught. Take this one, substitute here. Therefore IP of 0 is a into q into dp by LP into, our equation is p dash of 0. Now we have equation for p dash of 0, that is a into q into dp by LP into p dash of 0 just before we derived p of 0 minus pn naught. Now we need to calculate pn of 0. This is the next level. Okay, now I want to get this. Fine. Okay, now I am taking the help of law of junction here. So we know, or from law of junction, law of junction, Pp equals to Pn into e power V naught by Vt, V naught by Vt. This is the law of junction. For a biased junction, instead of V naught, we write V barrier. Okay. Now, so I am going to this. First, I am applying this one to a open circuited junction. For a open circuited junction. For open circuited junction. For open circuited junction, Pp is hole concentration in P region, that is approximately Na. Sir, here default I am taking P plus N junction, sir. P plus N junction, that is a default. And Pn value, hole concentration in N region is Pn naught, I am representing. Okay, and V naught no change and Vt as usual. Now from this, we can write Na equals to Pn naught into e power V naught by Vt. That is the equation. Let us take it as equation number 1. Now I am moving to biased diode. Biased diode. Okay, that is open circuited. Now in forward bias. In forward bias, same equation I am taking, but Pp, hole concentration in P region is whatever the two things here you need to consider. This is the junction, P region and N region. In P region, more number of majority charge carriers are there. At the same time, few holes are injected from N region to P region. Okay, holes are injected from, sorry, electrons are coming this side. Okay, no problem. Now it's okay. This Pp is no change. It is Na. Okay, because here why we discuss this one is from N side we are getting some electrons. Even though we are getting electrons, some recombination is taking place. But this is P plus N region. So in N region is lightly doped. Once it is lightly doped, the amount of carriers coming from N region to P region are few in number. So that's why compared to Na value, hole concentration, that is negligible. That's why we taken Pp is Na, and Pn, hole concentration in N region, is Pn naught. Hole concentration in N region is, already here you have Pp naught, sorry, Pn naught, and few holes are injected into this. Okay, now Pn is nothing but this much number of holes at junction. This much number of holes at junction. Total hole concentration at junction, that is P naught. Okay, so P of 0. Okay, and V barrier is contact potential minus applied forward voltage. Now by taking this data, substitute in this equation. Now it is Pp is Na equals to Pn is P naught into e power, here V naught under open circuit condition. Under forward bias we can take this one, should be in forward bias, that is V barrier. So V barrier is V naught minus Vf e power V naught minus Vf by Vt. Let us take this is equation number 2. Okay, now this is Na, it represents, it is this also representing Na. Now I am going to that. From first equation, Na value is Pn naught into e power V naught by Vt, and this is equation 1. Equation 2 is Na is P of 0 into e power V naught minus Vt by, sorry, V naught minus Vf, forward voltage, applied forward voltage by Vt. This is the second equation. See, both are representing same Na, just I am equating that. Therefore, Pn naught into e power V naught by Vt equals to P of 0 into e power V naught minus Vf by Vt. Just simplify this. It is Pn naught e power V naught by Vt equals to P of 0 into e power V naught by Vt into e power minus Vf by Vt. Now this one and this one gets cancelled, and take this one this side. Therefore, we can write finally P of 0 value as Pn naught into e power Vf by Vt. Vf by Vt. Here Vf is the applied forward voltage. Applied forward voltage. Okay. So far we get the value of P of 0. Now take this P of 0, substitute in your current. So our current equation is ID equals to A into, IP of 0 is A into Q into dP by LP into P dash of 0. So P dash of 0 we converted into P of 0 minus Pn naught. Now we got P of 0 value. Now just substitute that. A into Q into dP by LP into P of 0 is Pn naught into e power Vf by Vd minus Pn. Now just take Pn naught common. So A into Q into dP by LP into Pn naught taking common. Now it is e power Vf by Vt minus 1. This is the whole diffusion current at junction. Similarly, electron diffusion current at junction is In of 0, which is A into Q into dN by Ln into Np naught into e power Vf by Vt minus 1. Okay, now by some adding these two, you get the complete diode current. Therefore, diode current is IPN of 0 plus INP of 0. We mentioned this one here with the terminology IP of 0 and this one with IN of 0. Therefore, ID is, we know the values of these two, just substitute. ID is A into Q into dP by LP into Pn naught into e power Vf by Vt minus 1 plus In of 0 is A into Q into dN by Ln into Np naught into e power Vf by Vt minus 1. Now just I am simplifying this. Just take the common. This one and AQ are common now. Therefore, ID can be written as is A into Q, I am taking common, into dP by LP into Pn naught plus here dn by ln into np naught common into e power, this is the common is e power vf by vt minus 1. Now here the thing what you are getting, this total thing is taken as I naught, reverse saturation current. So therefore diode current id is I naught into e power vf by vt minus 1. Now I am taking, let vf equals to, I am representing by vd because it is id, diode current, diode voltage. Okay, now id is I naught into e power vd by vt minus 1, where I naught is a into q into dp by lp into pn naught plus dn by ln into np naught. This is the diode current equation, I naught, reverse saturation. But by applying some standards, we write diode current equation by id is equals to I naught into e power vd by eta vt. This is the new parameter I am adding, eta value, it is eta vt. Here eta is called ideality factor, which is 1 for germanium and 2 for silicon, and you can take 1 for silicon also for high currents. If diode current is high value, in that case you can take this value is 1 also for silicon also, high currents. Okay, now see this, eta is the ideality factor, it is 1 for germanium and 2 for silicon, and 1 for silicon also for high currents. What is the necessity to add this parameter is, see, theoretically whatever the value you calculated and practical value what you calculated, both are identical in case of germanium. In case of germanium, no change, both are identical. But in case of silicon, theoretical value and practical value are both are not equal. Both are not equal. To equating these two, an additional parameter eta is added. By taking 2 here, now the theoretical value of diode current and practical value of diode current both are equal. By taking 2 here, that's why we are introducing ideality factor at that point. Okay, so that is the meaning of eta. Okay, sir. Now see this. This is the diode current equation finally. So from this diode current equation, now a little bit time I am going to concentrating on I naught. So your I naught can be represented in different forms. This is the equation we are writing for I naught. I naught is A into Q, area of cross section, junction area, Q into dP by LP into PN naught plus dN by ln into np naught. Now, so here we know the values of Pn naught and Np naught. Pn naught is the hole concentration in N region So it is Ni square by Nd. Okay, and Np naught is Ni square by Na similarly. Just to substitute these values here. Therefore, the next form of I naught is A into Q into dP by Lp into Ni square by Nd plus Dn by Ln into Np naught, which is Ni square by Na. Ni square by Na. Now take Ni square common in this. Therefore, A into Q into taking Ni square common. Now it is dP by Lp into Nd plus Dn by Ln into Na. This is the reverse saturation current in terms of intrinsic carrier concentration. Okay, and we have another formula. So we have another relation, that is see, we know the diffusion length Lp, which is square root of dP into mu p, sorry, dP into tau p. Similarly, diffusion length L is square root of dn into tau n, dn into tau n. Now just take those two and substitute here in this equation. Now we get finally I naught value is I naught value A into Q into Ni square dP by Nd into Lp value is square root of dP by dP into tau p, dP into tau p plus dn by Na into Ln. Ln is square root of dn into tau n. So see this one cancelled in this by root times, this one cancelled in this by root times. Now it is I naught is A into Q into Ni square into 1 by Nd into square root of dP by tau p plus 1 by Na into square root of dn by tau n, dn by tau n. Okay, I naught is A into Q into Ni square. So 1 by Nd into root dP by tau p plus 1 by Na into root dn by tau n. That is the value of I naught. Okay, so these are the different forms of Ni. Okay, and we know d by mu is equals to Vt. D by mu equals to Vt. So you can write in place of dP mu p into Vt also, as you wish. That depends on the data what they given. You have to choose the right equation. Okay, now we substitute those things also here. So we know the value of dP, which is dP is mu p into Vt. Similarly, dn is mu n into Vt. Substitute this to dP and dn and mu n in this and take root Vt common. So I naught is A into Q into Ni square 1 by Nd into square root of mu p into Vt by tau p plus 1 by Na into square root of mu n into Vt by tau n. Just take root Vt common. So I naught is A into Q into Ni square into square root of Vt, taking common, into 1 by Nd into square root of mu p by tau p plus 1 by Na into square root of mu n by tau n. These are the different forms of diode reverse saturation currents I naught values. Okay, they may give in that different parameters are available here. So in problems they may ask, they may keep some parameters constant and some parameters variable. Okay, by properly studying the problem, you need to choose which parameter they given constant, and you can remove that, and you can relate the parameters which are variable. Okay, so that is the in general for a PN junction, A is constant, Q constant, Ni constant, root Vt constant. Okay, mobility constant, Na and tau. Okay, that depends on the data what they given. So these are the different forms of currents what we have, reverse saturation currents what we have. Okay, now I'm going back to the PN junction diode current what we got. Id equals to I naught into e power Vd by eta Vt. Okay, now so this is the current what we have. Id equals to I naught into e power Vd by eta Vt minus 1. Now this is, I am writing it as Id equals to I naught into e power Vd by eta Vt minus I naught. Now take this I naught this side, then it became Id plus I naught equals to I naught into e power Vd by eta Vt. And we know one thing, this is the diode forward current of the order of milliamperes. This is microamperes or nanoamperes reverse saturation current. So compared to this, it is 1000 times more. Okay, just keep that in your mind. Later we go and verify that. Now I am going to differentiating this current with respect to Vd. Therefore, dId by dVd plus 0, I naught is constant, 0 equals to constant I naught into e power Vd by eta Vt. Vd by eta Vt as it is I am taking into 1 by eta Vt. And one more thing, here we have this much data. From this you can write this is Id plus I naught. Therefore, dId by dVd is Id plus I naught by eta Vt. So compared to Id, I naught is very small. That means Id is much greater than I naught. Therefore, Id plus I naught can be written as approximately Id. Therefore, dId by dVd is dId by dVd is Id by eta Vt. We called it as change in output current by change in voltage, input voltage. That is the transconductance GM. So therefore transconductance GM is transconductance. Okay, so GM is this one. Now 1 by GM we call it as RD or R, small r, that is the dynamic resistance. Dynamic resistance. One by GM is dynamic resistance. So 1 by GM means dVd by dId. From this we can write 1 by GM value is eta Vt by Id. So dynamic resistance is finally dynamic resistance is Rd eta Vt by Id. Okay, these are the different parameters you can calculate from the knowledge of diode current equation. Okay, just to remind what are the things we discussed today. Okay, first we calculated the diode current. The diode current what we got is I naught into e power Vd by eta Vt minus 1, and where I naught is reverse saturation current, its value is A into Q into standard one dP by Lp into, so I am taking the in terms of Ni square here, 1 by Nd plus Dn by Ln into 1 by Nd. And after that, there is an important point here you need to note. They are given the value of P dash of 0, sorry, P of 0. P of 0 value also required, that is P of 0 is we got Pn naught minus, sorry, not this, so the injected, see this is the injected value, this one I want, this expression I want, that is injected value P dash of x, P dash of 0 it is P dash of x, it is P dash of 0 into e power minus x by Lp. This is very important, sir. In previous GATE examination they given a problem only on this injected hole carrier concentration or hole density. Injected charge density they ask sometimes. Charge density means just add Q to this. Injected charge density. Charge at junction. At a junction in N region. In N region. That is, just add Q to this. Q into P dash of 0 into e power minus x by Lp. They given a problem in previous GATE examination on this based on this equation. Q into P dash of 0 into e power minus x by Lp. That is the injected charge. That much amount of charge is injected into the region, junction. Okay. Now, at a junction in N region means no need of this one. In N region, this much amount of injected charge is present. Okay. Injected charge in N region, no need of junction. If junction if you use, you need to take x equal to 0. This is the injected charge in N region. Q into P dash of 0 into e power minus x by Lp. That's it. Okay. That is the equation. And after that we calculated the transconductance Gm. Gm is dId by dVd. It is Id by eta Vt. Id by eta Vt. And dynamic resistance Rd is 1 by Gm, which is eta Vt by Id. Okay. So these are the equations for transconductance and dynamic resistance. Okay, these are the different parameters related in when diode is under forward bias. Okay, so next session we go and calculate whatever the diffusion capacitance exists at the junction, we calculate that. Okay, And just a minute, I rewind these topics. Just see this. First we take in forward bias. In forward bias we operate the diode in circuit diagram and we operate it. Now external electric field is there. Results. This is the VI plot we get in forward bias. Okay. Now forward voltage in terms of the order of volts and current of the order of milliamperes. Okay, after that different current components present here we define. Okay, so the sequence of events taken place here is a drift or injection, diffusion and recombination. These are the sequence of events takes place in a forward biased PN junction diode. So next one is, so these are the different current components involved in a diode when it is in forward bias. Hole drift current in P region, electron drift current in N region, electron diffusion current in P region, hole diffusion current in N region. Now the different equations for diode current is ID is IPP of X, means hole drift current in P region, extreme end of P region. Similarly INN of X, that means electron drift current at extreme end of N region, and hole drift plus electron diffusion in P region. Similarly electron drift plus hole diffusion in N region. But at a junction it is the hole diffusion current and electron diffusion current. So I am taking this is the standard equation to calculate the diode current density. So diode current equation. Before going to that, in N region, once holes are injected into N region, what are the different equations, different relations present in that? I mentioned here. Okay, so here different relations what we measured is represented here. Now the name of each parameter is mentioned here, and after that diode current equation, just you mention IPN of 0, INP of 0. Now I am defining that current in terms of diffusion current density. IP is JP into area. So this is the whole diffusion current. Okay, now dP of X, already we defined P of X in previous equation. In previous equation this is the P of X equation. Now we differentiated this and substituted the value in that. By substituting the value and simplification, after simplification we got the diode current equation. This is IP of 0. Now finally after substitution, this is the equation we got. This one is the IP of 0. Okay, this is the whole diffusion current in N region. Whole diffusion current in N region. Sorry, whole diffusion current at a junction. This is electron diffusion current at a junction. Okay, they may ask what is the only this component, they may ask. This is whole diffusion current at a junction. Whole diffusion current at a junction. Similarly, this is electron diffusion current at a junction. At a junction. Okay, now sum of these two is the total diode current. So just I added these two. After simplification I got the diode current, and here I defined this part is the I naught reverse saturation current. Now we have different forms of I naught. Okay, so this is the I naught, and eta we are adding to that. This is the ideality factor. To equal the theoretical and practical value we are using the eta. In case of germanium it is 1 and in case of silicon it is 2. Okay, and for high current values you can take that value is 1 also, no problem. And after that we derived different relations for I naught, substituted PN naught value, and after that DP value, after that LP value we substituted, after that DP value we replace. Okay, like that after doing the different things we got the different relations for I naught. Okay, so in problem you may expect any one of this, but you should be thorough with all the values. And after that we taken the diode current equation and we calculated the dynamic transconductance and dynamic resistance. We derived in detail about dynamic resistance we discussed in VI characteristics and the temperature effect on the VI characteristics. At that time we discussed more in detail about that. and this is the dynamic resistance. These are the equations what we discussed so far today. Okay, so my dear students, please take a note of all these equations. Okay, you have the chance to rewind the video once again, and don't forget to take a note of these all these expression derivations. Okay, who are appearing for IES, for them these derivations are compulsory. For GATE students also required it is. Why? Because in early days they given the question based on the complete at the dead end whatever the equation, final equation we are deriving, only they concentrated on that. But in recent last 3 to 4 years onwards, they are concentrating, they are picking the, in our complete derivation part, they are picking one intermediate part, they are framing the problem on that part. So you should be thorough with all the derivations. Okay, so now thank you, thanks to one and all for spending your valuable time with me. So please don't forget to use my code VRAW10 during subscription. During subscription, don't forget to use my code VRAW10 and hit this bell icon to get the notifications. And please join our Telegram group for latest updates on our upcoming videos. And don't forget to subscribe. Please give your valuable comments on YouTube to strengthen ourselves and to provide a better quality data to upcoming students. Now, thank you. Thanks to one and all. Now, once again, I am welcoming you all to Unacademy, India's largest online learning platform. Okay, thank you. Thank you very much.